Okay, I'm going to go ahead and get started then. So hello, we will be presenting research on a novel path planning algorithm developed for applications in social navigation of human-populated dynamic environments. I'm Nicole Gunderson, and I'm a third-year student majoring in biomedical engineering at the University of Colorado Boulder.
I'm Akanksha Nalakanti, and I'm a third-year student majoring in aerospace engineering at the University of Colorado Boulder. We completed this project with the assistance of our PI, Christopher Heckman. To bridge the gap between robots and humans, there's a necessity for path planning algorithms for robots in human-populated dynamic environments. This work is built off other path planning algorithms such as A*STAR and RRT, but it presents a system that is efficient and has a low computational cost path, using novel methods of node generation and search methods. The main goals of this new algorithm are improved efficiency, adaptability, and safety, and each of them were addressed during the development of the algorithm.
This system has the possibility of bridging technical gaps that are currently preventing human-aware motion planning techniques from widespread, safe, and practical use. The development of this novel system can have potentially transformational effects within the fields of task and motion planning, industrial manufacturing, autonomous driving, and of course, social navigation. The improvement of efficiency and capability made possible by this work could have broad applications within the increasing number of robotic systems being deployed in public spaces, improving their adaptability, awareness, and safety. In order to accomplish this goal, we designed the program shown in the flowchart format below. Because our system is designed to operate over pre-existing node patterns, the great majority of our computation is to choose the most viable and efficient node paths from the surrounding nodes to the current location of the robot. The system ranks the cost of each considered node path based on a number of factors that determine eligibility. The first factor considered is the proximity of the current state location to the goal state location. If the current state is within close proximity to the goal state, given that there are no obstacles that lie in the way, a path will be drawn directly to the goal state from the current state. If the current state is not in close proximity to the goal state, the second least costly options will be considered. If the x position of the current state is to the left or right of the goal state, paths that drift towards the x position of the goal state will be favored. However, if the x position of the current state is equal to that of the goal state, moving straight forward will be favored. If there are no paths that fit these requirements, the path is allowed to move in the opposite direction of the x position of the goal state. If there are no paths that fit this requirement, the path is allowed to move backwards. And if there are no paths that fit this requirement, the path is allowed to move onto a previously chosen node or remain stationary. These more costly options are usually chosen to avoid a collision with a dynamic obstacle, and the path is generally able to remain efficient and maintain a low cost while avoiding both static and dynamic obstacles. This is a pseudocode representation of our algorithm, but it represents the exact same method of ranking the cost of each node path in order to promote efficiency and adaptability previously shown in the flowchart format.
Once the simple base of our algorithm was built, the first goal was to improve the node generation for the robot and to find what the optimal pattern of nodes would be. Initially, we decided to only check the 10 closest nodes to the current node for viability. This method allows the algorithm to only check small samples of nodes at a time for each current node, leading to efficiency. Eventually, this helps with the optimization of the backtracking method that was used to help the robot try and find a new path if it gets stuck between static obstacles. Alternatively to generating a selection of random nodes, sample nodes, throughout the environment and determining their viability and building a path, i.e. RRT and RRT star, we chose to explore predetermined non-random node generation. This method of node generation places a consistent pattern of sample nodes over the map between the start node and the goal node, regardless of viability of the nodes due to limited visual space, obstacles, or other constraints. This method allows path planning and collision avoidance to occur independently of node generation, which allows for efficient path planning. The algorithm only needs to test the nodes for obstacle, collision, and viability as they're being chosen. It does not need to generate new ones and throw them out at the same time. This leads to high efficiency, low cost path planning because only a small number of nodes ever get checked for viability.
Another important inclusion to the system is a path smoothing algorithm. Examples are shown here of the paths generated before and after their smoothing. For a dynamic planner, the design of a path smoothing algorithm comes with additional difficulties though. The planner must be able to navigate through dynamic environments, so the path must be smoothed almost as it is generated. The planner takes into consideration the motion and predicted paths of dynamic obstacles within a certain range of the goal state and smooths the paths generated within this radius. Currently, our system exists entirely in simulation, so a planner is able to generate paths and smooth through the entire goal state. The path smoothing algorithm uses a method called Bezier curves to smooth the paths. The general outline of how a Bezier curve is generated is shown on the screen. with each endpoint being defined as the chosen node points, and the control points as well as the maximum curvature are able to be adjusted depending on the locations of obstacles. The curves are generated with both dynamic and static obstacles being taken into account, and the use of this path smoothing algorithm allows for simplicity of deployment as well as generally decreasing the cost of overall paths.
Previously, we had planned to implement three-dimensional map generation using a program such as Octomap, and as our planned application would occur primarily in 2 dimensions, any filled voxel above ground would be assigned to be an obstacle. However, these programs are generally more complicated than what is necessary for our current application, but would provide more space to our program to grow for various environments and applications. We have come to recognize 2-dimensional mapping would be able to identify obstacles to the same dimensions as we're currently playing around in simulation. This would allow us to have simple integration as our current code would run as it does in simulation for real-world applications without many alterations. We started by learning about different 2-dimensional mapping algorithms such as Hector mapping and G mapping to find out what would be the best to implement our code with. After trying Hector mapping and G mapping independently, we found a Husky robot simulator that was integrated with ROS, ARVIS, and G mapping. The Husky simulator also allows us to use our path planning algorithm instead of the one that is being used in the simulator. Currently, we're integrating our algorithm from Python to ROS and learning how to alter our algorithm for a more realistic environment compared to what we have built with static and dynamic obstacles. The next step would be to do real-time testing with the Husky using the Husky sensing and perception tools to path plan through an environment that contains static and dynamic obstacles. As of right now, we're only simulating the dynamic obstacles in our algorithm, and it is not a part of the Husky simulator at all. Another lab is working on human and dynamic obstacle collision avoidance, and we're planning to implement our algorithm with their work when both teams are ready.
Okay, so to evaluate the performance of the system, we calculated the average time to generate a viable path, the percentage of viable paths generated, as well as the comparison of this general problem at the top of the slide that was presented within the sprint paper. The evaluations for our solution were taken from simulations where objects cover between 30 to 55% of the map, and all of our calculations include 3 dynamic obstacles. The calculated average time for our planner to generate a viable path was just below 0.6 seconds. The calculated average time, this number is comparable to that of other planners, with the most competitive being Sprint, with an average of only about 0.5 seconds, but that's only for 25% of the map being covered in obstacles, with no dynamic obstacles included. All other planners being compared had an average of above 1 second for only 25% of the map being covered with no dynamic obstacles, with some taking over 10 seconds. This point of evaluation is extremely promising considering our increased map coverage as well as the inclusion of dynamic obstacles increasing our computation cost. Additionally, when the program does fail, it is able to quickly identify when its current path is completely non-viable, taking an average of only about 1.3 seconds. So if a failure does happen to occur, the path is able to regenerate and create a complete and viable path in a lesser time than comparable planners. The planner is able to create a viable path over 90% of the time though, which is adequate considering the swift generation and regeneration speed. Additionally, the lengths of the generated paths are comparable to other similar planners, again shown by the top example. Generally, our path lengths of the system are longer than that of optimizing planners such as RRT Star and Stomp, which found higher quality path, but these results come at a significantly higher computation cost. The evaluation of these results fulfill our goals for the system, as the Percenta system is able to quickly and reliably generate viable and low-cost paths in both static and dynamic environments, in many cases more quickly and robustly than existing static planners.
Through the combination of node generation, obstacle avoidance, path smoothing, and real-life modeling simulations, our work has provided an algorithm that can eventually be implemented onto a robot. Our algorithm has achieved its goals of improved efficiency, adaptability, and safety. The improved node generation with the static and dynamic obstacle avoidance methods have increased the efficiency of our algorithm far more than expected. With the fast adaptability of the algorithm, it has the ability to mitigate risks and potential failures to choose the safest path possible, but not lose its efficiency. By executing the algorithm through the Husky simulator, we will be one step closer to the achievement of real-time testing with the dynamic human obstacles as well. We're getting within the reach of closing the gap between inefficient path planning programs with an algorithm that can be used to path plan in human-populated dynamic environments. We would like to thank Professor Christopher Heckman, PhD students Kyle Harlow, Mike Miles, and graduate student Daniel Torres from the Autonomous Robotics and Perception Group for their support and help through our research journey. If you have any questions, please feel free to ask us now or to contact us at these email addresses. Thank you so much for your time and have a great rest of your day. Thank you.
Okay, awesome. I think that our time is up, but if you guys had any quick questions, we'd totally be